Okay, so if you take a look at the diagram that you have on the screen, what exactly are you seeing in that little picture there? Who can give me an idea of what you're seeing in there? Okay, Tim.
You're seeing two speakers, A and B, that are both emitting sound waves.
Okay.
And they meet at point N.
Okay.
And I can't. Is it?
Okay, so far so good. So what Tim said was this: you have speakers A and B who are emitting what types of wave? Sound waves. Okay, so what's happening now is this. Let's pretend that you are standing at point O. So that's where you are standing. That's where the observer is standing. So when you are at point O, look at what it says. A listener standing at point O, which is located 9 meters from the center of the line connecting the two speakers, hears the sound intensity at its maximum. So if you hear a maximum at point O, what type of interference might be happening at this point? Constructive interference. Okay, so far so good? Now, all of a sudden, the person at O decides to walk over to point N. So you're walking over to point N. Now, when this happens, when the listener walks to point N, the sound intensity now reaches its minimum. So when you get to point N, all of a sudden, what happens? You get destructive interference, which means that if you have destructive interference, what is going to be created at that point? Some kind of somebody said it? It's got to be a node. Okay, so far so good? So let's put that destructive interference right about there. Okay, so you have a destructive interference point at that node, which is why I labeled it N. Okay, now the question is, if you get destructive interference at point N, what must be true about the sound waves from A and the sound waves from B? Something must be true. And if you take a look at the diagram, let's see if we can compare the distance that sound must travel from A to N to the distance that sound has to travel from B to N. What can you say, Rebecca?
The difference between the two lengths they have to travel is half a width.
Excellent. So I don't know if you guys all heard that or not, but what she basically said was that if you take a look at the difference in the path length between between A and N and B and N, that difference must be equal to 1/2 of a wavelength. So could I actually say this? If I were to measure AN, can anyone tell me what that measurement might turn out to be? Tim?
9 meters.
9 meters. Is there some way that I can figure out the distance between B and N? And if you look very carefully, you might see a Caroline. Pythagorean theorem. So can everyone see the right angle triangle here? Okay, so we know what this side over here represents. Between A and B, we're separated by 2.5 meters. A and 9 meters. So if you take a look at the hypotenuse, using Pythagorean theorem, I think some of you probably did the calculations. It turns out to be approximately 9.34 meters. Okay, so the question is, how much further did sound travel going from B to N compared to A to N? What would you say the path difference is equal to? Say that again? 0.34 meters. So what we're going to say now is this. 0.34 meters would be how many wavelengths? 1/2 of a wavelength. So if you take a look at the equation now, what would you say that one full wavelength must be equal to? Yes?
0.68.
0.68 meters, or 68 centimeters. Okay? Are we good so far? Anthony?
If BN was 9 meters?
If BN were 9 meters?
Yeah,
okay.
Just assume it was. Does that mean it would be constructive? Or like the wavelengths would be equal?
Exactly. So I don't know if you guys heard what Anthony was saying. Hypothetically, if BN turned out to be exactly 9 meters and AN were also 9 meters, what can you say about what happens at point N? It has to be constructive interference. So what would you hear at that point? A minimum or a maximum? A maximum. A maximum what? Okay, when you say sound, what part of sound? Maximum amplitude. Okay, so far so good? But because we have destructive interference, now you get minimum amplitude. So what happens to the sound altogether? It kind of disappears. I don't know if you guys have ever been driving in your parents' car. You know when you're going on a long trip up Highway 400, let's say. Every now and then you're listening to your favorite radio station. And all of a sudden, let's say what's your favorite, 97.6 or something, whatever station you're listening to. So you're listening to your favorite music, but all of a sudden, after a couple, let's say, several 10, 20, 30 meters down the road, what happens to the reception that you get from your radio? Kind of goes away. It gets all fuzzy. But then if you drive another 30, 40 meters later on, it reappears, right? Why would it disappear then reappear? Well, if you take a look at radio towers, this could be one tower, that could be another tower. So when you're driving along Highway 400, when you get to this point, tell me about the radio waves from these towers. They are constructively interfering. But when you drive 34 meters further north, here the radio waves are destructively interfering, and so on and so forth. Does that kind of make sense? Okay, so what we've just done right now is we've answered part A of the question where it says how much further do sound waves travel from speaker B to speaker A. All right, from speaker A to N and speaker B to N. So we answered part A, but then it says part B. If the speed of sound in air is 345 meters per second, what is the frequency of the tone emitted by the speaker? So let's just move this up a little bit. Oops. All right, so let's answer part B. What do we know right off the bat? What's given in the question? Let's see if I can get somebody else to answer this question. Okay, Ethan, what else is given in this question?
V.
Speed is, okay, sorry, hang on a second. It's good. V, speed of sound, what is it? 345 meters per second. So is there any way I can now find the frequency of the tone that's being emitted? Yes, who can help me out with this one over here? Anthony.
You can just use wavelength, which is 0.68 on your calculation.
So I can use this value and that value. What's the one equation I might be able to utilize? V equals frequency times lambda. If I'm trying to find frequency, what might frequency be rearranged to become equal to? V over lambda. So if I work this all out, can we agree 345 meters per second divided by 0.68 meters? And if I move this up a little bit there, if I now solve for frequency, what do you end up with as your final answer? 507 hertz. And there's your final answer, and that's it. Okay? Now, if you take a look at this question, if you had to rank this in terms of level of difficulty, what would you rank this to be, approximately? Everyone just blur out some numbers there. A 2. I think right now you would say a bit on the lower end, but when you first saw it, maybe a little bit difficult. So again, I think it all comes down to how you interpret the question, what exactly does the question mean, and identifying what they're really asking you to find. You might have some kind of a receiver and an emitter. So let's just say, okay, 680 News. You want to find out your traffic aware. 680 News has a tower somewhere in Toronto. In fact, they may have 3 towers in Toronto. Let's just say, okay. But let's only take a look at these 2 for now. So here's the thing: if you listen to the radio 680 News, and your friend in Pickering were listening to 680 News as well, would you and your friend hear the exact same thing at the exact same time? Actually, yes. Yes, and here's why. You would hear, in other words, if I'm listening to the traffic report right now, guess what your friend in Pickering is doing? Listening to the exact same thing at the exact same time. Now you might say, but sir, that's not true because radios give you sounds. You're listening to sound waves. Well, usually when you listen to the radio, you're listening to what's coming out of the speakers, correct? So what's coming out of the speakers, depending on how far you are from the speakers, yes, you might be hearing slightly different things. But tell me about the sound that's being emitted from the speakers. They're the exact same thing at the exact same time. Why? Guess what radio waves happen to be? These are radio wave towers. Okay? Now, let's say you live in a house over here. I'm just giving you an example. So you have a house over here, and let's say you have your own little radio inside your home. So you have okay, so there's your desk, and there's your radio. It's got a big speaker there. Yeah, it's a red radio with a speaker. So, and here you are, you're listening to the radio. Now, how do signals get to your radio? The antenna, right? So what happens in this case is that you get, yes? Yes? Now wait a second, what are those little green lines I drew? What kind of waves? Light waves, okay? These are radio waves. Radio waves are a type of light wave. Well, light travels at what speed? only one speed, 300,000 kilometers per second. Okay, or 300 million meters per second. Same thing, right? The light only travels at that speed, which is more or less instantaneous. In other words, as 1 second goes by, when 1 second goes by, so okay, let's count 1 second. Ready? And go. 1. So in that 1 second, light traveled how far? 24 and a half Earth diameters. So do you know what if you think of the diameter of the Earth, not the radius, the diameter of the Earth, so think of 24 and a half Earths, like side by side by side. Light traveled that far in 1 second. Okay, do you guys understand what I'm kind of saying there? So hang on a second. And again, we can calculate this, but we won't. But yes.
How long does it take to get from the sun to Earth?
I believe it's approximately 8 or 11 minutes. I keep forgetting which one it is, but I think it's 8 minutes. I think it's about 8, yeah.
How did they figure this out?
Oh, very easily. Because if you look, speed of light is 300,000 kilometers per second, or 300 million meters per second, right? Well, guess what the radius of Earth turns out to be?
So, like, how did they figure out like the speed of light?
Okay, that's a different story. Well, we're gonna, yeah. But if you take a look, I'll just do the quick calculation. Guess what the radius of Earth happens to be? All right, 6.38 times 10 to the power of 8 meters. But that's the radius. Well, how do you find the diameter of Earth? You multiply that by 2, right? So watch this. C represents the speed of light. Speed is equal to, last time I checked, distance over time, right? So let's take a look at this for a second. Let's set time to be 1 second, okay? If I set time to be 1 second, and I already know what the speed of light is, could I find out what d turns out to be? Yeah, it would just be equal to 3.0 times 10 to the power of 8. Well, let me just move this over a little bit. Okay. All of this multiplied by what? 1 second, right? 2.
Well, like, don't you multiply the radius with not that?
D is equal to C times T. So I just want to know how far light in 1 second. All right. So would this turn out to be 3.0 times 10 to the power of 8 meters? Okay, now that's how far light traveled. If I divide this now by 2 times 6.38 times 10 to the power of 8, guess what that turns out to be approximately? It's either 24.5 or 23.5. Somebody do this for me. Okay, I'll do it. 3 exponent 8. Sorry, my apologies. I made a slight miscalculation. It's not 6.3 times 10 to the power of 8 times 10 to the power of 6. It turns out to be 23.5 Earth. Sorry, my mistake, 1 less Earth. Okay, so light travels 23 and a half Earth diameters. Okay, now that's very far, right? So could you say then that if in 1 second light travels 23 and a half Earth diameters, then